We want to prove that S5 is not solvable. So we start first with simple groups. So a group G is simple if its only normal subgroup is identity and the group itself. So there are no groups in between. So only thing you have is either the trivial identity element or the group itself. So let us give an example. So say you have a cyclic group of prime order. This P is prime, and this is simple. Now simply because the only subgroups of this are identity and the group itself, and you can form the series. This 1 is a normal subgroup of Z over PZ, the cyclic group of order P, which is prime, and therefore this is solvable. So there are no groups in between. So only group you have is identity and the group itself. So now a very important theorem which will be useful. So a solvable group is simple if and only if it is cyclic of prime order. So we have already proved this direction. So we have shown that this is a cyclic group of prime order and this is a simple. So there are no groups in between. Yeah, because you do not have any non-trivial subgroups of any group of prime order, because if you have a non-trivial subgroup, that will have to divide the prime number, which would be a contradiction. So now we have to prove in this direction. So say you have a solvable group and it is simple, then we have to show it is cyclic of prime order. So you have this group G and it is solvable, so you have a series like this. So you delete any repeats in the series so that Gi plus 1 is not equal to Gi. So therefore you will have Gn minus 1 is a proper subgroup of G. But we are saying G is simple. G is simple, that means its only subgroup is 1. So Gn minus 1 is just 1, the identity. So G is anyway equal to Gn, so you can write G by 1 is equal to Gn minus 1, because 1 is Gn minus 1. So G is equal to Gn over Gn minus 1. So this is abelian, because that is a property of a solvable group. You have a series and the quotient like this of consecutive terms is abelian. And since G is abelian, every subgroup of G is normal, since G is abelian group, and every element of G generates a cyclic group. But G does not have any non-trivial proper subgroups. Precisely because G is simple, we are given this statement and we are proving in this direction. So we are given G is simple, so it does not have any non-trivial subgroups. Now if it does not have non-trivial subgroups, it must be the case that G is a cyclic of prime order. So G is cyclic of prime order, because if it has a prime order, then there is no number which divides this prime, so you do not have any non-trivial proper subgroups. If n is greater or equal to 5, the alternating group AN is simple. So this theorem we will prove later. It is a long proof, but let us see a consequence of this theorem. So we want to show that Sn is not solvable for n greater or equal to 5. So in particular, S5 is not solvable. So we have shown in a previous lecture that subgroup of a solvable group is solvable. So we start with the assumption that Sn is solvable, and we will reach a contradiction. So we will reach the conclusion that Sn is not solvable. So we are starting with Sn is solvable. So since alternating group is a subgroup of this permutation group, this An would also be solvable, because An is a subgroup of Sn. Now An is solvable. So this theorem says that An is simple. So now we know An is simple, and we are saying that An is solvable. So An is simple and solvable. So that means that it is a cyclic of prime order. So a solvable group is simple if and only if it is cyclic of prime order. So we are saying An is solvable, and we are using this theorem that An is simple. So these two combined with this theorem now tells us that An should be cyclic of prime order, but order of An is n factorial divided by 2. Now this is not prime for n greater or equal to 5. So you can see, n factorial itself consists of factors, and you just cancel out one of the even terms. Maybe just cancel out 2. 1 2 all the way you multiply till n, this 2 cancels out, but you have so many factors, so it is not prime for n greater or equal to 5. So since it is not prime, that means it cannot be an cannot be solvable, or we cannot start with this statement that Sn is solvable. So there is a contradiction right here. Sn is solvable, so therefore Sn is not solvable. So now we want to prove this big theorem. If n is greater or equal to 5, the alternating group An is simple. So first notice that An is generated by 3 cycles. So 3 cycles are of the form this ABC. You can write it as AC times AB. So recall that An just consists of even number of transpositions. So all even number of transpositions can be made from these 2 transpositions, and you adjoin them all together, you get even number of transpositions. So An is generated by 3 cycles. So now you consider a normal subgroup n of An, which is non-trivial. It's just not simply identity. So we will show 2 things. First, we will show that if n contains a 3 cycle, then it contains all 3 cycles. So n would be equal to An, because An is generated by 3 cycles. So if n contains a 3 cycle, we have to show that it contains all 3 cycles. Now second part is to show that n contains a 3 cycle. So then we are done. So if n contains a 3 cycle by second part, then by first part it contains all 3 cycles and n is equal to An. So we have to show this first 1. So let us show 1. So suppose that n contains a 3 cycle, and we have to show now that it contains all 3 cycles, and therefore n will be equal to An. Because n is a proper subgroup of An, if it contains all the generators of An, then it has to be equal. So suppose n contains a 3 cycle, and without loss of generality, say 1 2 3 lies in n. So for any k greater than 3, this cycle 3 to k lies in An, because it's a 3 cycle. So now recall for a normal subgroup, G inverse Ng is equal to n. So here this G is drawn from our group An, and we are using this here 3 to k inverse 1 2 3 3 to k. Compute, you will get 1 k2. So this implies that 1 k2 lies in a normal subgroup, just using this formula right here. So since this normal subgroup is closed, you multiply this element by itself, you get 1 k2 square is 1 2k, which again lies in normal subgroup, and again k is greater than 3. So for n equals to 3, we are done. We don't have to do anything, because A3 itself is a cyclic group. For n greater than 3, and say A and B greater or equal to 3, you consider this permutation. This lies in An because this is an even number of transpositions, 1 transposition and 2 transpositions. So 2 transpositions. So again use this formula. This obviously lies in the normal subgroup, which we have shown here. So this now ABK lies in n. So all 3 cycles are of the form ABK. So therefore n contains all 3 cycles. Since An is generated by 3 cycles, we have An is equal to n. So we have shown that if n contains a 3 cycle, which we took as 1 2 3, we could have taken anything, but 1 2 3 is easy to deal with. This is a constructive proof. We showed that all these cycles of the form ABK also lie in n. So we are done. So we do this problem case by case. So it is here in part 2 that we are going to use this n is greater or equal to 5. So n is at least 5. And we are going to show now that n must contain at least 1 3 cycle. And then we will be done. We will be able to show that An is simple if we are able to prove 2, because then the only normal subgroup of An is 1. There is no non-trivial normal subgroup. Any normal subgroup which we choose for An would be exactly An. So we do this case by case. So case 1. So say n contains an element, say x, and this x is made up of these permutations, alpha, beta, gamma, and so on. And all of these permutations, say alpha, beta, gamma, are disjoint cycle, and the first permutation is made up of this a1, a2 all the way to am, where m is greater or equal to 4. So now we are using this n greater or equal to 5. So first case is that our first permutation contains at least 4 elements, so contains a 4 cycle. So now you choose t as a1, a2, a3, and then our normal subgroup contains t inverse xt equals to z. So because this is a 3 cycle, so this t lies in an, and again we are using this standard property that g inverse ng is equal to our normal subgroup. So this g is taken from an because it's a 3 cycle, so you put t inverse xt and you denote this by z. Then this z lies in the normal subgroup, so z lies here. So what does the z look like? So z you have obtained by multiplying t inverse here and t, so putting t inverse here and t at the end. But all these cycles are disjoint, and this t contains the elements a1, a2, a3 which just lie in alpha. So this t will just come all the way here, because t is not going to impact any of the elements in these disjoint cycles. It is only going to impact any elements in alpha, so it goes all the way to here. So z looks like t inverse alpha t beta gamma. So z lies in the normal subgroup, and we are saying that x lies in the normal subgroup. So since n is a subgroup, it contains zx inverse. So if you write zx inverse, it will be of the form a1, a3, am. So this is just computation. So this is a 3 cycle. So for case 1, if n contains a 4 cycle like this, then n will contain a 3 cycle. So it contains at least one 3 cycle. So we have been able to prove 2 for the case 1. So for case 2, now we say n contains an element with at least 2 3 cycles. So we are saying at least 2 because if it contains one 3 cycle, then we are already done. So we are saying at least 2 3 cycles. So without loss of generality, say this x lies in n, and x is of this form 1 2 3 4 5 6 kappa, where kappa is disjoint from 1 2 3 and 4 5 6. So kappa does not impact 1 2 3 or 4 5 6. So it does not permute these elements. So set t as 2 3 4. So then t inverse xt again like this. So t is a 3 cycle, so t lies in an, again because it's an is generated by 3 cycles. So again use this formula. So this portion lies in n by this formula, and x we are saying already lies in n, so x inverse lies in n because x is a subgroup, so it will also contain the inverse of the element. And when you compute it, it gives you 1 2 4 3 6. So just computation by hand. So we are saying this will lie in n, so product of 2 elements in normal subgroup would lie in the normal subgroup. But now in case 1 we have seen that there are 5 elements here. If you count that there are 5 elements here, so if there are more than 4 elements, then n contains a 3 cycle. So if this lies in n, then n would contain a 3 cycle by case 1. So we are done for case 2. So now case 3 is, so n contains an element x which is of the form, you have a 3 cycle, but this 3 cycle is multiplied by rho, where rho is the product of 2 cycles, and these 2 cycles are disjoint from each other. So obviously it cannot be a single element, because if it was a single element, then you already have a 3 cycle. So we have to show that there is a 3 cycle inside n, but we are taking an element of this form. There's a 3 cycle and there is a product of 2 cycles disjoint from each other. And so these 2 cycles are not only disjoint from each other, they're also disjoint from ijk, so it does not impact ijk. So then you take x square, you multiply this with itself. Since rho is a product of two cycles, it's just transpositions, so you multiply transpositions with each other, they will cancel out, so the transpositions will go away if you multiply this element by itself. So only thing would be left is square of this. So you apply this to itself, you get ikj. So x square, since x lies in n, x square lies in n, so now you have a 3 cycle which lies in n. So that's what we had to show. So n must contain 1 3 cycle. So we have considered greater or equal to 4. We have considered 2 3 cycles. We have considered a single 3 cycle and 2 2 cycles. Now let us see that another case 4, where element is of this form, this 1 2 3 4 gamma. So there are transpositions and a gamma, and we can write this because n is greater or equal to 5. You can write like this. So this case could exist, and we want to show that such a case would not exist, and therefore you will just lie in case 1, case 2, case 3, which will give you 3 cycle. So such a situation would not arise. So let us see this. So we have written like this, and gamma is disjoint from the previous two. So gamma does not change 1 2 3 4. So it just fixes these elements. It has no impact on them. So set t equals to 2 3 4. So if you set t equals to 2 3 4, you again use this formula. So t inverse xt, this will lie in our normal group. X already lies in the normal group, so x inverse also lies in the normal group. You multiply this, you get 1 4 2 3. So now you choose u as 1 4 5. Again, u would lie in an because it's a 3 cycle. An is generated by 3 cycles. Again the same trick. U inverse xu would lie in n. Again the same formula. X inverse lies in n. This gives you 4 5 2 3. Simple computation. So this element lies in n because it's a product of 2 elements lying in n. This element lies in n because it's product of 2 elements lying in n. Now multiply these two. So if you multiply these two, do the computation, you get 1 4 5. So this 1 4 5 now lies in n, but we started by saying that n consists of these 2 cycles which are disjoint from each other. But see, 1 4 5, if you decompose it, it becomes 1 5 1 4, and these two are not disjoint. They have this element 1 in common. So this contradicts our assumption that elements could be of this form. So there are no elements of this form. So you can safely say such a case does not exist. Only case of the form 1, 2 or 3 exists, and in these 3 cases we have shown that n contains at least 1 3 cycle, and therefore we are done with the proof. So for n greater or equal to 5, the alternating group an is simple.